All right. So yesterday we used our different types of hybridization to construct double and triple bonds, which we now know exist as sigma and pi bonds, or perhaps a sigma and 2 pi bonds. And depending on the number of lone pairs and bonding pairs, that ultimately determines our hybridization, which then ultimately determines the electron pair arrangement for that particular atom. So the hybridization determines that electron pair arrangement, and ultimately we can get the shape from it. And that's where we're heading. We ultimately want to talk about shapes of molecules. You might think that we're already there, but we're slowly constructing the scaffolding needed to in order to explain this. So it turns out that there is more types of hybridization than the 3 that we've learned, SP, SP2, and SP3. And that's what today's lesson is on, introducing you to what we call the expanded valence shell and the fact that some atoms, and when I say some atoms, I'm talking about atoms in the 3rd row and below, they can have more than 8 electrons in their outer shell. So let's just get straight to this. Atoms in the 3rd row and below have access to d orbitals and can form hybrids with them as well. 2 lessons ago, when I introduced you to hybridization theory, one of the important aspects of hybridization theory is that when you add the orbitals together to form your hybrid orbitals, those subshells must be from the same energy level. They must have the same principal quantum number, 2s and 2p, for example. And I stated that you couldn't hybridize with then, say, the 3s along with the 2s and 2p. So you can only put together hybridized orbitals that come from the same energy level. And the reason for that was the wave size becomes so much different when you go to the next energy level that when you add those waves together, you really don't get much of a change. It really doesn't result in a useful wave function. Taking that into account, if we're dealing with atoms then that are in the 3rd row and below, those atoms can form hybrids using the 3s, the 3p, and even though these subshells are not filled in this order, the 3d are available for hybridization. So even though if we were building an atom and we were to get to, say, argon, and we were then go to potassium, yeah, the next electron goes in the 4s before it goes into the 3d. In terms of hybridization, an element like sulfur, yes, it has 3s orbitals, it has 3p orbitals, but then it also has these 3d orbitals, and they can be incorporated into hybridization and into hybrid atoms. So that's what we're doing at this point. We're going to expand our hybridization. Not only can something like sulfur be sp hybridized, which it can, sp2 and sp3, but it can also be sp3d hybridized, where it takes in then one of those d orbitals and forms a 5th hybrid orbital. Okay? So that's what this is all about. And any atoms I'm just going to bring the whole thing up. And any atoms that are in the third row or the third period or the third energy level and below can do this. So something like phosphorus. Phosphorus has 5 electrons in its valence shell. In normal atomic phosphorus, we have 2 electrons in the 3s orbital and 3 electrons in the 3p orbital. It looks much like a nitrogen. That phosphorus can undergo sp, sp2, sp3 hybridization, depending on what's bonding with it. But it also has the ability to undergo something called sp3 dehybridization. And it's very easy to determine how many orbitals there will be. It's right in the name, S, 3 Ps, and a D. So there are 5 of these sp3d hybrid orbitals. Now I've drawn in the 3d orbitals that are unhybridized. Could we have some kind of wild pi bonding going on between those lobes of those d orbitals? When you get to atoms down in here, sure you can. You can have all kinds of weird bonding going on because they have 4 lobes, right? Like a clover leaf. You can have them overlap sideways. You could have d orbitals forming pi bonds. We are not getting into the complexities of that. All right, but you could have them. We're just going to deal with sigma bonds that take place with these expanded octets. Okay, so let me just check my next slide because I used to know what it was this morning when I looked at things, but the CAN brigade, I've forgotten what I'm doing. Okay, so I'm going to switch again to here, and we are going to, actually, before I do the example, I want to draw just what the representation of sp3d orbitals would look like, okay? And I would like to do it on the board. Actually, I will do it on the board first. And yeah, and then I'll show you my little shortcut here. So in sp3d hybrid orbitals, there are 5 separate orbitals, and they look like this. One of them is in the plane, all right? You could draw this. And 2 of them are also in the plane, as if we have a triangular planar structure. So it looks a lot like our sp2 hybrid orbitals, where there's 3 of them, and they're in a plane. And that's the same here. One goes in behind, and the other one comes out front. All right? And those 3 form a planar structure. So there's 3 of our 5 orbitals. Now the other 2 orbitals, they actually look a lot like a p orbital, right? So they actually look a lot like this unhybridized p orbital in our sp2, but the main difference is that unhybridized p orbital is 1 orbital, can only handle 2 electrons. And in this case, they are 2 different orbitals, up and down. All right? And they are perpendicular to that plane. 90 degrees in there. Okay? This picture looks a lot like our sp2 hybrid orbitals, but the main difference is in sp2, the planar orbitals are the hybrid ones, 1, 2, 3 orbitals, and then the p orbital is a fourth orbital, and that's it. There's only 4 of those. You can only put 8 electrons around that hybrid situation. In this case, there is 1, 2, 3, 4, 5 orbitals, and you can put 2 in each, which means surrounding an sp3d orbitals, an atom that is sp3d hybridized, you can have 10 electrons around it. And that's why we call it the expanded octet. It can now have more than 8. It's breaking the octet rule. Okay? Now, I don't know if anybody's absent anymore or not, but it doesn't matter. In terms of my video, just so that I can complete it, looking at the orbitals, I've created, what the heck's the matter with my finger here, working on this device, doesn't work. Okay, I have created, and it is the program, excellent, it's great when technology fails miserably. That is frozen. There we go. So, in my hybridized situation, you notice I've got an sp3d here. Let me just pull it out here. And again, I've tried to kind of represent that. We've got 3 in the plane, and then we've also got the 2 above and below. All right. And the big thing about this thing is that there's 2 main types of angles, and you can put this on your picture that you've just drawn. All right. So in this picture, we have here 120 degrees. There's 120 degrees separating what I would call the equatorial orbitals, as if we're treating it like a globe. We're saying that the triangular planar ones are in the equator. And then we also have here 90 degrees between the polar orbitals and those equatorial orbitals, every one of them. So in this case, there's 90 degrees. Okay? All right? So this is, the hybridization is sp3d. You probably have that written somewhere. But let me now draw the EPA, the electron pair arrangement. How do we describe this particular shape? We describe this as a pyramid, right, with a triangular base. All right? So we call that a trigonal pyramid, but there's 2 of them stuck together, top and bottom. I don't know, can you see it? Can you imagine that we've got a pyramid in here, right? With that being the top down to those, right? See the pyramid? And I've got a second pyramid stuck to it on the bottom. So there's 2 pyramids. We call it a bipyramid for 2 pyramids. So this is called a trigonal for triangular, trigonal, bipyramidal. What a fabulous description. Trigonal bipyramidal. 2 triangular-based pyramids sandwiched together. 120 degrees between each of the adjacent equatorial orbitals and 90 degrees between the polar orbital and an equatorial orbital. Okay, that's pretty exciting stuff. So that's what we get if we have 5 identical, well, they're not identical, but 5 orbitals. They're as identical as they can get. And we call that sp3d hybridization. So let's go back and do that example that I was just talking about. What was it, pH5? pH5. Now in tomorrow's lesson, I'm going to review how we do Lewis structures for what we called ugly ones. Remember, we called them the ugly ones? But you know what? We've got all kinds of ugly ones now. Because I told you 2 days ago that for boron and beryllium, they don't need to follow the octet rule. And so now you're going, oh man, I'm going to have to now memorize that beryllium only needs 4 electrons around it and boron only needs 6 electrons around it to be happy. So those are now exceptions to the octet rule. I told you that hydrogen is an exception because it only gets 1 line. You guys do that one, that's an easy one. Now I'm telling you, any atom in the 3rd row and below have the ability to follow the octet rule, or if there's extra electrons around, it can have more. So not only can it have 8, it might have 10, it might have 12 electrons around it. There's even structures that I've heard of that have 14 electrons around that central atom, which means that octet rule that we've been telling you since grade 9, 8 electrons. Every atom wants 8 electrons. It's really a special case, only those atoms that want just 8 electrons. There's really only 3 or 4 atoms that have to follow the octet rule. Carbon, nitrogen, oxygen, and fluorine. That's it. Everyone else can have an exception, which doesn't make it an exception anymore. But that's the way it really exists. So now we need to come up with ways to be able to draw the right Lewis diagram, and I'm going to show you how to do that tomorrow. But essentially the same thing. We really should be adding our valence electrons. 5 valence electrons for phosphorus, and 5 times 1, and I've got 10 electrons around that thing. So now I'm going to build the skeleton like I did before. This is a little preview to what we're doing tomorrow. It's actually exactly what we're doing tomorrow. I could even probably get rid of that lesson. And now I'm going to have 1, 2, 3, 4, 5 H's around it. Now here's where you say, uh-oh, the octet rule. I can't do that. But now you got to remember, uh-oh, phosphorus is in the 3rd row and below. Sure it can. If it's in the 3rd row or below, it can have an expanded octet. Theoretically, it could hybridize all those d orbitals. That would make it s, p3, and then what do I need? 5 more of them? It could have 2, 4, 6, 8, 10, 12, 14, 16, 18. You could have up to 18 electrons around those things. Now, those structures don't really form very well because when you start jamming so many atoms around one atom, it gets a little busy. And it can't actually fit. It starts to push them away. So they become unstable when you try to jam that many of them in. Well, phosphorus is in the 3rd row and below. Excellent. So we are allowed to have 5. So I'm going to do my analysis like I do. And I'm going to have 5 bond pairs and 0 lone pairs, which means I have 5. And because it's in the 3rd row and below, I'm allowed to have S, P3, and a D. So therefore, it is sp3d hybridized, and the EPA, and I'm going to write that up here because I want to do an energy level diagram. The EPA is trig by peer, and that's the way I shorten that up, right? So we've got a trig plan, right? Trigonal planar. This is a trig by peer, trigonal bipyramidal, triangular-based bipyramid. Now let's do the energy level diagram, and it's really not that exciting. Phosphorus, we go back to neon, and because I have 5 and I need sp3d, 1, 2, 3, 4, 5. I'm not worried about the extra D's. Told you I could teach really fast. So let me slow things down a little bit. Phosphorus in the 3rd row, it can have more than 4 bonds around it. It can have an expanded octet. I do my exact same analysis and I get 5. That means it's got to be sp3d, which means here I need to have 5 circles because I have those 5 orbitals that we created. sp3d. How many valence electrons does phosphorus have? And you might think, oh no, I don't even know how to think about that. That's basic rules from before. Yep. There's 5. And they will be spread out in here. 1, 2, 3, 4, 5. And now I'm going to attach 5 hydrogens to them with sigma bonds. 5 of them. And if I'm not writing that little H in there, this is exactly how I'm going to do it. I'm going to just put a whole bunch of s orbitals in here so I can make, and so these are all H's, right? I think we get the idea that these are all H's, right? Those are all H's. No problem. Nope. So again, the orbital view. I'm going to grab one of my sp3d. And now I'm going to just put on my 1s's on the end of this thing. Okay? And now the 3D Lewis, and I do have one that I can grab off of there, but I'm going to draw it so you can see how I draw this. With the 3D Lewis, again, all you need to do is imagine what those lines down the middle of those orbitals will look like. All right? Those are terrible lines, but we've done this, already. So in this case, phosphorus in the middle. One bond heading up north to the pole, one heading down south to the pole. And then it doesn't matter which way you head with this. I know what I've got on the board is 180 degrees rotated from this. Doesn't make any difference, but I'll make it look the same as this one. Over here, that's in the plane of the paper still, right on the page. This guy here's got to come out front, so it's going to be a wedge. And this guy has got to go in behind a little bit, so it's going to be a squiggle, squiggle, squiggle. And I'm going to make this H maybe a little bigger than this H so I can give it a little bit of perspective. And we have our 3D Lewis diagram representing a trigonal bipyramid. Okay? Now, like I said, in theory, those third row and below can expand all the way to have all of those d orbitals incorporated into them. But I'm only going to teach you about sp3d and sp3d2, and then that's it. That's all we're going to go into. Yep. To use with F's and all that stuff, according to hybridization theory, that is a legal move. So you can have all kinds of wild hybrid orbitals, right? But we're talking about jamming them around a single nucleus. And like I said, if you then try to squeeze other atoms, and you're trying to now squeeze more and more atoms around a single nucleus, they all start to repel each other away because they all have electron clouds around them. So as you try to squeeze more and more pairs of electrons around a single nucleus, it becomes physically impossible, right? It comes to a point where they repel each other away so much that the force of repulsion of the adjacent orbitals and nuclei and atoms that are there is greater than the force of attraction due to the overlap of the sigma bond. So it becomes energetically not functional to have that many other nuclei jammed around one single nucleus, and therefore we don't see them exist in nature. Theoretically, according to hybridization theory, you bet you could add them up all day long mathematically. Okay? Same with the fact that I'm going to stop at sp3d2. And that's because there are all kinds of examples of sp3d2 hybridized compounds. I've heard of a handful of sp3d3 ones, but I haven't read any information on anything that has any more than that sp3d3 than 7 of them around a single nucleus because it's jammed way too tight. And it would have to be hydrogens because as soon as you put a fluorine on the end of that, it's bigger. And if you try to stick maybe a bromine on the end of it, the bromine is huge. So again, it becomes pretty busy around the nucleus. Okay, let's talk about the last type of hybridization. Yeah, you can write that down. That's kind of defining the expanded octet. I think I've said it enough times, but this kind of makes it official. So yeah, like I said, carbon, nitrogen, oxygen, and fluorine are the only ones that must follow the octet rule. Isn't it great? We hammer you and we hammer you with, everyone must have 8, except hydrogen. And now it's like, everyone can have 8, right? Everyone can have 8, except hydrogen, boron, and beryllium. They don't have to have 8. And then everyone in the third row and below can have more than 8 if there's enough atoms around to share with. So the next hybridization is sp3d2. In this case, I'm using sulfur with 6 hydrogens, sulfur hexahydride, I guess. Oops, sorry. I'm getting ready to draw my picture here. So next I'll draw a picture again. First I'll do it on the board so that you can see me the way I would do it on the board, how you might do this in your notes, and then I'll put my quick version up there. So now I'm going to have 6. And you can think of how the picture is going to look by thinking about what happens when you have to add an extra orbital filled with electrons. Every time another orbital is added on here, they all have to kind of move around in order to give space for that orbital. All right. You can imagine that the trigonal bipyramid is kind of formed by taking a tetrahedron and trying to maybe stick it in the bottom part of this tetrahedron. And if you do that, you stick it in the bottom, then that's going to cause those legs of the tripod to push up a little bit, right? Because they've got to make some room. They're going to be repelled away. And then you can think of the bottom legs of the tripod kind of stretching out to become the planar part in the equator with now another orbital stuck to the bottom. And so the same thing here. If you try to stick another orbital in here, right, it's going to try to go where it can have the most space. Where do you think it's going to be inserted where it can have as much space as possible? Because notice I've got 2 angles in here. I've got 120 there, and then I've got 90 degrees there. So there's actually 2 different spots I could stick this thing. Where do you think it might go where it's going to have the most space to fit? Yep. Between 3 and 4, or between 1 and 3, or between 4 and 1, because these are all 120, right? If I try to jam it between, say, 5 and 1, that's 90 degrees. That's a smaller angle, which is why we're going to do yoga. That's a smaller angle than the 120 degrees. So if you're going to stick it anywhere, it's going to go in the equator somewhere, all right? And when that happens, it's going to push them all around a little bit, and we're going to result with 90 degrees between all of them in the equator. So it's going to look like this. Up, and I'm going to get different colors here. Down. So there's the polar guys. They haven't changed whatsoever. I know I've changed colors, but that's my up and down. And now I'm going to have one coming out of the board and one going in behind. Out and in behind. And I'm going to have the other guy coming out of the board and another one going in behind. And you might say, and they should be the same size. I didn't do a great job on that picture. You might say, hey, that looks just like 3 p orbitals. That looks like 3 regular unhybridized p orbitals. Px, Py, Pz. But the difference is in 3 unhybridized p orbitals. So that's just 3 orbitals. There's just 3 of them there, and only 6 electrons can go in them. In this situation, we have 1, 2, 3, 4, 5, 6 orbitals, and 2 electrons can go in each one. And so we can have 12 electrons around this thing. With my little simulation, again, I've already designed an sp3d2. There it is there. I've got all different colors on those, attempting to represent up and down, in behind, coming out front, in behind, coming out front. And if we were to look at the angles on that thing, then we're going to have down, up, in behind, out front, in behind. You can draw that on your picture that you have over there. And in this case, I don't have to distinguish between an equator and a pole because all the angles are identical now. All the angles are 90 degrees. Every orbital is perpendicular to the neighboring orbital. So 90 degrees, attempting to put a little bit of perspective on that 90-degree thing there. And same with up and down, 90 degrees. Again, I'm attempting to put a little perspective on that 90 degrees. They're all 90 degrees. So there's really we really don't have to worry, like with the trigonal bipyramid, all right? There's a difference between the equator and the poles, and we'll see that when it comes to naming the shapes later on. But with this guy, there's no difference. Now, naming the EPA for this guy, you might think if this is a trigonal bipyramid, then goodness, I've got a square-based pyramid, and there's 2 of them. You might think it's called a square bipyramid, but it's not. In this case, if we were to connect all of the corners down to the orbitals, all right, and do the same on the back side, all right, you end up, and then you connect all these in here. What a great shape. You end up with these triangles, 8 triangles, right? On each pyramid, there's 4 triangles, right? And so the top has 4 triangles, the bottom has 4 triangles, and the shape that's made up of 8 triangles is an octahedron. Just like a shape that's made up of 4 triangles is a tetrahedron, this is an octahedron. And don't ask me why we don't call this a hexahedron. I have absolutely no idea. I'm just going by what they tell me. Ask the geometers. Can you be a geometer? I want to be a geometer when I grow up. Making shapes. I don't know. All right. So the EPA is octahedral, an octahedron, 90 degrees between each of the adjacent guys. And I think you probably got this labeled down here, by the way, the hybridization is sp3d2. Let's do our example. So that was sp3d. That was my example. I'm heading back up here. So now I'm going to put, what was it, SH6? SH6. Oh, barely going to make it. Crazy can brigade. Again, Lewis diagram. We'll be going over this, but I think we're getting the hang of it like we did last year. 6 electrons from the sulfur. 6 times 1 gives me 12 electrons. Put the central atom. In this case, because sulfur's in the 3rd row and below, we can put as many lines around it that we need to. We don't have to stop at 8. So 1, 2, 3, 4, 5, 6, and we'll put H's on it. And I do my regular analysis. 6 bond pairs, 0 lone pairs. We're going to find with tomorrow and on Monday that I can have things that have 4 bond pairs and 2 lone pairs. That'll still get me 6. That'll still get me sp3d2. Or I could have 3 bond pairs and 3 lone pairs. That's still sp3d2. I'm just introducing them to you so I have only bond pairs so that we can see the shape of it. But any combination, just like we saw the other day, that gets me 6 will result in sp3d2 EPA octahedron. We'll just put here oct. Again, I'm teaching you how to do the whole analysis of a compound right from top to bottom. That's why we do the same thing over and over again. You're finding with the homework it might just say, what's the hybridization of the following molecules? Then all you got to do is get to here, right, and you're done. Right? But I'm showing you the whole procedure. Energy level diagram, sulfur, I think neon, is it? Neon, 1, 2, 3, 4, 5, 6, as dictated by the sp3d2. 1, 2, 3, 4, 5, 6. And you'll be thankful that I'm sticking hydrogens to all of these, because if I made them all fluorines, you'd have to have like that last p orbital with 1, so you'd need an s and all the p's, and you'd need 6 of them. Think of the picture, it would be chaos. So we put it all with hydrogens. These are all representing hydrogens. If you need to put the H in there to help you remember, you can do that. I'm making these a little more circular and these a little more oval so that we can distinguish between a hybridized orbital and the non-hybridized S. Sigma bonds all around. Orbital view, and I get to cheat, and you don't. Too bad. And then I'm going to put a bunch of O's around it. Again, we want to get to the point where you don't need to worry about the orbital view, because once you get to that shape, once you get to that EPA shape, you should be able to draw a 3D Lewis. But I think the orbitals are just so pretty. Like I said, they're like flowers. That means all of our bonds holding our bodies together are really made up of little flowers. That's so I can get in my hippie frame of mind for the molecular geometry yoga. Because really, I'm a hippie when I get home. This is just a show for you guys. All right, 3D Lewis diagram. 3D Lewis diagram can be done a couple of ways, but there is one standard way of doing it, and it's very much like the picture that we were doing with our orbital view. We have sulfur, and up and down get straight on the board right there. And then just like with our trigonal bipyramidal, the only difference is I've got 2 of those on either side. One coming out front, one going in behind, one coming out front, one going in behind. So one coming out front, one going in behind, one coming out front, one going in behind. H, 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 H. Can we see it? Can we see the octahedron? 90 degrees and all? If you can't, right, you can imagine that we got this type of action going on here. There's the square in the plane, right? And then we've got those 2 pieces in the top. Okay? So that is octahedral. That is sp3d2. You can have an sp3d3. I've looked it up because somebody asked me one time, can you have an sp3d3? Yeah, you can. I checked it. I wasn't sure. That third or that 5th orbital, or what am I at to? 1, 2, 3, 4, 5, 6. The 7th orbital, because they're all 90 degrees, could go in wherever it wants. And what it does is it will go in between. We can imagine it going into the equator here, and then you've got a pentagon in the equator. And I don't know, would you call that a pentagonal bipyramid? I don't know. Maybe you would. But that's what the structure is. That's what they see that structure as being. All right? We're not going to worry about pentagonal bipyramids. Okay, now I do have a couple of example questions I must get through. Let's not worry about this. We've already done this. I did another summarization, but let's quickly go through this. Let's quickly go through this example. And this stuff isn't in the textbook. It actually isn't even in the curriculum, but I think it's really cool. And you're going to have to learn it next year anyway. So, hey, come on. It's fun stuff. You'll thank me. That's what you'll do. You'll come back at Christmas after a fabulous first term of chemistry, and you'll say, thank you. And I'll say, you're welcome. Anyway. I think it's really cool. Like, here's the thing that I think that we need, why we need to do this. At the very beginning of this chapter, we learned how to use electron configuration to explain why something like iron can have possible charges of 2 and 3. We now can explain that, right? Your grade 9 teacher says, oh, by the way, iron can have 2 charges. And you're like, what? Why? Well, don't worry about that. It just can. And then in grade 11, you guys all want to use all of the numbers that are like associated with sulfur and chlorine. But it says plus or minus 1, 3, 5, and 7. And I say, just use -1. I say, forget about those other ones. Just don't worry about it. Now we can answer the question. Now we can explain why sulfur and phosphorus and chlorine and bromine have all these extra possible charges they can have. So sulfur can have a valence of 2, 4, or 6. That's on the periodic table right there. It can have -2, all right? If it gains 2 electrons, that's boring, but it can have also 4, 2, 4, and 6. If it's sp3 hybridized, sulfur, neon, sp3 hybridized, 1, 2, 3, 4, sp3. How many valence electrons in a sulfur? 6. So because we're not using those other Ds, they're way up there in the higher energy, it's going to go in 1, 2, 3, 4, 5, 6, which means it can form a bond here and a bond there. It can form 2 bonds. Therefore, it has a valence of 2. It can give away, not give away, but share away those 2 electrons. Depends on the electronegativity, whether it has more control or it's giving them away. sp3 dehybridized. Sulfur, neon. sp3d means how many ovals am I going to have? sp3d, 5 ovals. 1, 2, 3, 4, 5. sp3d. How many valence electrons? Still 6. That's a trick question. Still sulfur. Still has 6. But now there's 5 orbitals. 1, 2, 3, 4, 5, 6. Which means it can form bonds here, 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 and here. Sorry, that's not even in the right spot. There. I don't know why I did that. It was terrible. In each of those unpaired, it can form a bond. It can have a oxidation state of 4. And we've just seen sulfur in its sp3 D2. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And I'm not going to put little arrows with each of those. You can see there that all 6 electrons are available for sharing. So hybridization explains the multivalence of our nonmetals. We've explained the multivalence of our metals with electron configuration and how they give away their electrons. Now we've explained the multivalence of our nonmetals. Time is ticking. It's going to fit perfectly. Now, like I said, because the textbook doesn't have any questions, I'm giving you some questions. And you can write them down. I think you got time to do that. If you don't, it's online, right? It's the last slide in the more, whatever this was titled, more hybridization or whatever we called it.